Hello, everyone, and welcome to the talk about Python with NumPy on GPUs. My name is Paweł Pomorski. This is my email if you would like to contact me. So Python is very popular among researchers because it's easy to use, which means that it's easy to put together code quickly and test your ideas. But it's not really built for performance, so it's slower than compiled languages in general. So one very commonly used method to avoid this problem is to use a library such as NumPy, which provides an interface to mathematical functions and arrays. And behind the scenes, it uses compiled libraries for the numerical computations. So there is no or little performance penalty. And in recent years, GPUs have arrived on the scene and they offer a great deal of computational power. So a natural question arises, if you have a Python code which uses NumPy, how would you transfer this code to run on the GPU to get the computational power that a GPU provides? Now, as a further justification for this, it's worthwhile to note that we at the Alliance are increasing the amount of GPU power that we can offer. So in 2025, we are replacing 4 of our systems. Only Narvel from the original clusters is going to be still around. And all 4 of the new clusters have very powerful H100 GPUs in them, quite a large number. So, so if anything, there's even more incentive to consider transferring your work to the GPU. Although we have to keep in mind that these GPUs will be in very high demand. There will be lots of people trying to run jobs on them. So even though they offer a lot of computational power, you have to keep in mind that there will be a long lineup, and it's not a given that transferring your work to the GPUs will actually speed up your workflow. Because of course, these new clusters will also contain a large number of very powerful CPUs as well. But nevertheless, I think everybody should, if you are using Python and NumPy, you should at least spend a little bit of time considering how well would it do on the GPUs. So learning GPU programming to actually program them at a low level, of course, is quite involved because it's a quite different computational device than the CPU. We, in fact, offer a summer course coming up in our summer school to teach you that. But the goal here is just to do as little work as possible. Ideally, we would just like to take our NumPy code and run it on the GPU with almost no changes. And the 2 software packages that I will be talking about, which allow you to do this, are CuPy and cuPyNumeric. So CuPy is a drop-in replacement for NumPy. So basically, you take your NumPy functions and you rename them to CuPy functions with very little change otherwise, and then your program runs on the GPU. However, this approach does require memory management because, as you will see, GPU and CPU, they have their own memory, and you do have to transfer data from the CPU to the GPU and back. So that's CuPy. And then cuPyNumeric aims to be a complete replacement where you don't need to do any code modification. So you just take your NumPy code, you change where you're importing NumPy from, NP, and then you run, and with no changes, your code will accelerate on the GPU. So this looks easier, but this, as we will see, there are some small drawbacks compared to CuPy with this approach. And these are the links you can check for the documentation on both of these. So just a few brief words about GPUs. So we are not going to be writing any GPU code. We want to avoid this completely. But you still need to know just a few basic ideas about what GPUs are, because that will explain the performance that we will be seeing. So the first issue is that a GPU is a massively parallel device. So whereas your CPU has, I don't know, 8 cores, 16 cores, our cluster GPUs have 64 cores. The new clusters will go up to 128 or even more. The GPU has thousands of cores, so it's a massively parallel device. So in general, that means that the problems you run on them have to be big so that you give all those cores something to do. So basically, if your matrix is too small, you're not going to get any benefit out of running matrix operations on the GPU, or relatively little benefit. So that's one thing, and we will see how this impacts performance. And the other issue is that the GPU has a separate memory. So to achieve this high performance, the GPU must be accessing data located in this separate memory. And so there arises the problem of memory management, of defining some arrays on the CPU, in the CPU memory, and some in the GPU memory, and then transferring the data between them. So this adds some additional lines in your program. So it makes your program a little bit more complex, but more importantly, there's a performance cost to this transfer because the bandwidth between the CPU and GPU, it's not that great. I mean, it's getting better over time, but it's still relatively slow in most GPUs you'll be using. So there's a cost. So that means that you have to take this cost into account and basically make sure that it's not significant for the problem you're solving. So before we convert our NumPy code to the GPU, it's always a good idea to optimize it first. So run it, rewrite it so that it's as efficient as possible, even on a CPU. And of course, in this talk, I can't really go into how to do this in any great detail, but the key idea is that you must eliminate explicit loops. So you can't have any for loop over your NumPy array because that's going to be quite slow. And it will also prevent us from transferring our work to the GPU, especially with cuPyNumeric, because cuPyNumeric basically doesn't allow you to use explicit loops. There's a huge performance penalty if you use explicit loops. And so once your NumPy code is optimized, you also want to profile it to identify the region where it's spending the most time. And you want to consider transferring those to the GPU, because clearly those are the ones that you need to speed up. So again, I won't be talking about Python profiling here. I hope you can get this information elsewhere. And throughout this talk, I want to use a simple illustrative example just to show you what the code looks like and what the performance looks like. So let me talk you through this example. It's a very simple one. We are just solving a partial differential equation. Well, in 1D, so it's a differential equation. And we are solving the Poisson equation where we have the second derivative of u. That's the solution we are looking for. And then on the right hand, and that second derivative is equal to some given function b of x. So we want to find out what u is given b. We are going to solve this using a finite differencing scheme. So we discretize the function on the grid. So instead of a continuous u, we define values of u on points of the grid. And here I'm simplifying. I picked such units so that this equation is as simple as possible. So grid spacing is 1 and so on. The boundary conditions are u is 0 at the edges of this one-dimensional domain. And once I discretize, I can re-express this equation as this, where basically this expression is an approximation for the second derivative. So first, you might remember, first derivative is the slope of the line, and the second derivative is the rate of change in the slope of the line. So we get this kind of an equation. And finally, we can express our problem as a linear system with some matrix A with entries corresponding to these, multiplying the vector u, which is the discretized u on the grid, and this is equal to b. And then we can solve this system for u. So given A, given B, we can solve for u. And we are going to solve this by just using a standard linear algebra solve. This is actually not the most efficient method to solve this problem because the matrix here is highly sparse. Most of the entries are 0, so there are better techniques. But just for the sake of this seminar, we are going to take this inefficient approach. So, so we basically have to create this matrix A, which expresses this equation, the left-hand side of this equation. And this matrix basically looks like this. So here I have the case for a 4-4 matrix just to make it easy to draw. So we are going to have on the diagonal, we have -2. And then above the diagonal, we have 1s. And then below the diagonal, we have 1s. And the rest of this matrix is 0. So looking at this matrix, how would you create it? Well, if you wanted to use for loops, which of course there's a strong temptation to do because they are quite simple, you would define a matrix of zeros, n by n, and then you would just do 3 loops. So one loop would iterate over the diagonal and set this to -2. Then you would have one loop iterating, one to the right of the diagonal and set that to 1. Of course, the range being not n but n-1. And finally, we iterate to the left of the diagonal. So this seems tempting. And you might even say that this wouldn't be that costly because the matrix is n by n, but this loop is only over n. So the scaling isn't that bad. But in practice, I would strongly discourage you from doing this because we want to avoid using explicit loops at any cost, even though this loop is not that expensive to do. So let me show you the trick to do this without loops. So we are basically going to be using the identity matrix, but shifted in our computations. So the first thing I do here is I use the identity matrix function of NumPy. So this creates a 2-dimensional identity matrix, but I reshape it into 1 dimension. So then it becomes just a vector. And I can also, so I know what the matrix is supposed to look like, right? So if I reshape that in 1D, this is what the matrix looks like. So sorry, it's hard to highlight, but this line here, this is what I want the matrix to be. So I need to construct it from other matrices. So I'm going to do this in 3 stages. Of course, first, I can consider just the -2 entries, but this is just the identity matrix times -2. So here I define the identity matrix. I change the shape to make it 1-dimensional. And then I initialize my final matrix A with -2 times this 1-dimensional identity matrix. And then I have to shift. So I can see that, let's consider these points first, the points to the right of 1. You can see that this looks like an identity matrix just shifted by 1. So let me do this. So I'm going to take the identity matrix, but I'm considering it's shifted by 1 to the right. And then similarly, these points to the left, that's the identity matrix, but shifted once to the left. So I'm going to take the identity matrix and shift it 1 to the left. So this graph then shows how things are lining up. And I hope you can see that what remains for me to do is, so I just have these 3 1-dimensional arrays, which I need to add. So basically the interior points. And if I add them up, I will get the actual matrix that I need. So this is precisely what I do here. So I do use slicing. So I slice to only consider this subsection of the matrix of the array, so not the endpoints. And then I increment, so I use what was there previously. And then I take the identity matrix, but this is the identity matrix. This is this matrix, which starts off, so it's not shifted, but we, because it will start off here, which actually lines up with the first point. But I want to ignore the last 2 entries because, well, they are out of bounds. So I set the upper limit to be n2 -2, where n2 is n squared. And then this matrix, I have to shift it to the left. So I'm going to start from position 2. So I'm going to start from this position, which is going to match the position 1 in the way we are slicing. But anyway, so what I end up doing is I add basically 3 modified identity matrices, and I get the final matrix. And then at the end, I just have to reshape it back to 2 dimensions. So that's what I do here. So you can see with this trick that we can avoid using for loops, and instead we use slicing and shifting to get what we need. So let's look at the actual code for our problem. It's nice in Python that I can fit it all on one slide. So I import NumPy, import the time because I want to time how fast my code is running. Set n squared identity matrix, so initialize A. And also I need to initialize B with something. So I just give it, some kind of a Gaussian function. Gaussian, it could be anything. And then, so at this point, I have my matrix A defined, my matrix B defined, and I can run the solve routine from the linear algebra package inside NumPy. And I time it. So I take a timestamp before starting this function and a timestamp after, and then I print how long it took. And after this, of course, I could work with the data I got. I could plot it. I could save it to files. I'm not showing that part of the code. So let's look at the performance of this code for different matrix sizes. So I start off with matrix size 1000, nothing below that. On the reasoning that, well, if the matrix is smaller, it probably, it won't be a significant computational problem anyway. So, we don't have to spend too much time thinking about this. So this was tested on a Narvel CPU node, which has this processor. And so here I measure for N1000 and 2000 for 8, 16, and 32. So this is how long it takes. And here I look at the relative time. So let's say this is 6.3 times, takes 6.3 times longer than this. This takes 7.9 longer than this. So actually, it's not relative speed up. This should be relative time. I'll correct this in my slide. So this is a matrix solve. So we expect it to square as n cubed, the dimension of the matrix. So we expect, since we are doubling the matrix size at each increment, that means that 2 to the 3 is 8. So it should take 8 times longer. And it's not uniformly 8, but it's roughly 8 times longer as we double the system size. And this is the log-log plot of these same numbers. And here it's basically clear that, yes, there does seem to be a very, very smooth linear increase. And so it's behaving as expected. So the main point here is that for this kind of a problem, because it scales as n cubed, the computational difficulty increases rather quickly as you increase the matrix size. So I should also mention that there I was running with a single core, but NumPy does support parallelism through multi-threading, at least some routines. So this is a very convenient parallelism in that you don't need to modify your code at all. You just need to start it. So first of all, you need to be inside the job where you requested multiple CPU cores. And the number of these cores should be at least as high, well, ideally equal to the number of threads you'll be using. And then you just run your code with specifying OMP num threads. That means that you'll be using OMP threads. And also this flag is going to help improve performance somewhat. So here I picked a fixed matrix size of 16,000, and I tried running with various numbers of threads. So it takes 70 seconds with one thread, 36 with 2, 18, 10, 6, 5, and then 4. And here I can look at the speed up. So the speed up here means how much faster are we running? So for example, here with 2 cores, we are running 1.95 faster over 1 core. Then with 4, it's 3.74. With 8, 6.85. However, we see that our performance starts deteriorating, and this is to be expected. So with 16 cores, we would like this number ideally to be close to 16, but it's actually quite a bit below. It's 10. And with 32 cores, we are well below 32. We would hope for 32, but it's only 13. And then we do progressively worse with 64. This has to do with the fact that these cores, while they're all running at the same time, they are competing for resources. So for example, they are competing with each other to access to memory. So the speed up, cannot be linear as we ideally would want. But I highlighted these numbers in bold just to emphasize that if you are getting that kind of a speed up, you should not be running with this many cores, because if you are running with 32 cores and you're only getting speed up 13, you're using our systems inefficiently. So, and also that means that your jobs will take longer to start and so on. But I wanted to show these results because when we are comparing to the GPU, I am actually going to be showing comparisons to single core results. But of course, you should consider that you wouldn't necessarily run with a single core on the CPU. You would hope to run with multiple cores to speed things up a little bit at least. All right, so this was NumPy. So this was by way of introduction, basically. And now let's talk about CuPy. So how would we take this NumPy code, which I've shown you, and run it with CuPy? So preliminaries, you would have to install CuPy and NumPy in the virtual environment. on our systems, we have wheels for both of these. So just pip install no index, our standard approach will work. And then you need a GPU to run these calculations. So of course, there's no GPU on the login node. So you have to either submit a job via SPatch or ask for an interactive job via Salog. So then once you're in an environment where GPU is available, in your code, you import CuPy as CP. You replace the routines which you want to run on the GPU. So you change some of them from NP to CP. Then these routines on the GPU will need to use GPU resident arrays. So we need to define those arrays, move the data. And always important to remember that for efficient programs, the time spent moving this data must be significantly less than the time spent computing. So this is what memory management looks like. So first line is a standard NumPy array, so the NP array, and we call it underscore CPU just to emphasize that this array lives on the CPU, but of course you could call it anything you like. And then if I wanted to create a similar array on the GPU, I would just have CP instead of NP. So here I am creating an array of the GPU holding this data, and I call it x underscore GPU just to emphasize for myself that it's on the GPU. So how would you move data from CPU to the GPU? So if you want to go, so this is actually from CPU to GPU. Sorry, this should be the other way around. So so you do CP as array, and then you take your CPU array, and then this creates a GPU array with that data. And similarly, if you want to move data the other way from the GPU to the CPU, it's CP as NumPy, where you provide the GPU array, and this goes to the CPU array. And finally, if I want to run functions, NumPy functions, so here I have a norm function, which is coming from NP, and I take the CPU function here to get the result. And if I want to do the same thing on the GPU array, I provide a CP function, the CuPy function, and this produces the CuPy result. So generally, if you are using a CP function, you have to provide a GPU array, and if you are using an NP function, you have to provide a CP array. In practice, for some simple operations, you might actually get away with providing a CP array to a GPU function. It seems to be supported for some simple operations, particularly norm in my tests. But in general, you always want to make sure that a CP function gets data from the GPU. All right, so let's look at our NumPy code. And here I take the previous, I'm taking the previous NumPy code and I'm converting it to CuPy code. So this code will be a mix of NumPy and CuPy. So I'm going to keep some things on the CPU, those things which don't take a lot of time, basically the setup of the input of the initial matrix. But then the linear solve, I'm going to move that to the GPU. So actually here I am importing both NumPy and CuPy. I'm also importing the time function from standard NumPy. And finally, I'm importing a profiler toolkit from CuPy, which will be necessary, so we'll see. So the first part of the code is unchanged from the NumPy because, as I mentioned, we are just going to reuse the NumPy codes to generate the initial matrix A and B. But then I need to transfer my data to the GPU. So I do copy as array, where I take A and B, and I put them inside these arrays, and the sArray function of CuPy will return a GPU array. So I put this on the GPU, A and B. This line is strictly speaking not necessary, but it's good practice. This just detects a GPU. But this also hints at the ability of CuPy to actually work with multiple GPUs, because if you have multiple GPUs available on your machine, then you could define arrays on different GPUs and run them concurrently. I'm not going to say more about this, but this feature does exist. And then let's skip this line for a second. And here I could run my linear solve with A GPU, B GPU as inputs using the CuPy function. And the final result is an x underscore GPU. I could time this using standard Python timing. And finally, if I want to do something with this array x, write it to file, plot it, whatever, I need to copy it back to the CPU. So I do CP as NumPy. This takes the GPU array and it returns it as a NumPy array on the CPU. So in terms of changing our code, we had to add these 3 essential lines to move the memory. But otherwise, all we had to do is replace NP with CP in our code. Now, there is a problem here with timing because the CPU and the GPU, these are 2 separate devices. So the CPU can do one thing and GPU can do something else. In particular, a CPU could, let's say, call a function to tell GPU to start running that function and then not wait until that function is done, but actually keep going. Which means that when we are timing a code like this with CuPy with standard time calls, this might be unreliable. So this might give us basically too short a time estimate, less than the real amount of time it takes to run this function on the GPU. So the way to get around this is to use a benchmark tool from CuPy, where you provide a function that you're calling and its arguments. You could even say that how many times you're going to repeat it. And of course, repeating is good if you are measuring short time intervals, because then you're going to hopefully be able to average out the fluctuations. And this will give you both time on the GPU and the CPU. It will give you time measured by a timer on the GPU, which is going to be highly accurate. And here I'm actually, this code, I'm not showing all the code, but I can also repeat this calculation even on the CPU if need be. All right, so how do I actually run this? So I have to get hold of a GPU. So I either do a job script, submit job with SBatch, or get an interactive job via Salog. So inside it, I source my environment. I also have to load the CUDA module that's required for things to actually run. So I ran my CuPy code, the ones I've shown you. And here I did 1,000 repeats because it's a pretty small matrix, so it runs pretty fast. I averaged that. So the time as measured on the CPU is this. And then the time measured by the benchmarking tool is 3.3183 microseconds on the GPU and 227 microseconds on the CPU. So at least in the benchmarking tool, when it measures it's on the CPU, it basically just measures the time it takes to start the function. So it's not actually the relevant time. This is the relevant time. This is how long it takes to run the function on the GPU. And notice that in this case, we are actually lucky in that this actually matches pretty closely. I mean, this is 3 milliseconds, right? The 3,000 microseconds is about 3 milliseconds, and this is in seconds. So it's actually pretty close. But that could be fortuitous. We can't really rely on the time measured with a standard CPU clock. You should always use this benchmark if possible. And there's actually a way to not use the benchmark. You can use CuPy timing, which times on the GPU. It's just more code lines, but you can do it. I'm just not going to show it here. Okay. And then the other key thing, though, is are we keeping the GPU busy? This is always a very important question. So as I mentioned, the GPU has thousands of cores. So if we have a matrix which is too small, it's just not going to occupy all the cores. So how can we check how busy our GPU is? So there's a very nice tool called NVTop, which is basically like the top tool for CPU programs, but for a GPU. It is available in our clusters, and the way you use it is if you start running a job, whether interactive or SBatch, which uses a GPU, you can then open a second terminal and you can see which node your job is running on. So if it's on Narval, it's going to be ng some number, and you can just SSH directly into that node. And once you are inside this node, you can run NVTop. And what NVTop, so here I am running NVTop, and it gives you a time graph, which basically shows how busy the GPU is. So here, in this particular case, I started my GPU program about 10 seconds ago, and I can see the percentage utilization. So I can see this is going up to about 86%. I mean, this gives me a quantitative number. So I can see here that if I am running a matrix which is only 200 by 200, I am using my GPU at 86%. And then if I increase the size, I go up to 500, I go up to 95%. And when it's 1,000, I go up to 98. Now, of course, you might be tempted to say, okay, I'm already hitting 86%. So that's pretty good. But that's actually misleading, as we will see, because filling up the cores, it's a bare minimum to get your GPU running efficiently. So essentially, if this number is below 100%, you know that your GPU is not being efficient. And once it hits 100%, it might actually be efficient, but we will have to see. But anyway, this is a good argument why we should start with matrix size 1,000 and not even consider going below that. So this is the actual performance. So this is the speed up of CuPy over NumPy for matrix size from 1,000 to 32,000. So here are the times for NumPy. So this is same results as before, and here are the corresponding time for CuPy. And here I'm showing the GPU speed up. So for matrix size 1,000, the GPU is only 5 times faster. 2,000 is 14, 4,000 50, 8,000 163, 16,335, 32,498. So you can see that the speed up is increasing. And this is the plot of the actual scaling. So this is the CuPy result at the bottom and NumPy result at the top. So this is what I was showing you in the previous graph. And these are the times for CuPy. So how do we understand this? How come this speed up is actually increasing? Which means that if you look at these numbers, they are not scaling as the numbers for NumPy did. So it's not the case that, for example, this takes 8 times longer than this, and this doesn't take 8 times longer than this, it's less. So the reason is that clearly for matrices which are smaller, we are not saturating the GPU. We are not giving the GPU enough work, because on the GPU, you actually want to have more threads running. So you need to have at least as many threads as you have cores. But in fact, you need even more for efficient access to memory. It has to do with latency, hiding, and such things, which I will not go into here. But I hope you can see that the performance benefit really starts showing up at large matrix sizes. And the bigger the matrices, the more performance you're going to get. So for example, in this case, for these matrix sizes, it's not really worthwhile to use a GPU because, I mean, sure, it's 5 times faster, and 14 times faster, but we could see that we could get that kind of a speed up, running with multi-threaded Python just on the CPU. And, GPUs are in high demand, so your job generally has to wait longer to use GPUs, and it's just not worthwhile to wait longer just to get a 14-fold speed up. But of course, once we hit 50, that's better. And once we hit, over 100, then it becomes really beneficial. And like, especially if you consider, let's say, 500, because as we have seen, even if you run with multi-threaded Python with, let's say, 64 cores on a compute node, you're going to get less than 20-fold speed up, right? And this is 500. So we are talking about very significant speed up even over using a full node of Narwhal. All right. So and why is it so fast? I mean, I actually had to do a double take when I saw this number 500. Like, this seemed to be too good to be true. I had to double check all my calculations and sort of convince myself that it is true. But one thing which convinced me is we can see in very fine detail how the GPU is utilizing its architecture. And in particular, newer generation GPUs like the A100, which is on Narwhal that I'm using here, it has what are called tensor cores, which are specialized units for accelerating matrix operations. And clearly, CuPy library is making use of those cores. And you can actually check whether those cores are being used by going to the Narwhal portal. So this is the address. And when you go there, you will be able to see all your jobs. And then particularly, you can click on your job and see GPU utilization. And this gives you a breakdown of the use of various subcomponents of the system. In particular, here we have tensor GPU cores, this green line. And we can see that as I'm running my job, these cores are being used. So our program is accelerated on this piece of electronics, which is just designed to use to do matrix operations. And keep in mind that our older GPUs did not have those, but our newer ones do. All right. So let's move to the second approach, cuPyNumeric. So that approach is relatively simple because you just run your NumPy code with basically no modification except just a few lines. So I'm actually going to talk more about the setup, how to actually set things up on our system so that they can use cuPyNumeric, because the actual code conversion is sort of trivial. But the main thing is, as I already hinted at before, to use cuPyNumeric, your NumPy code must be efficient and it cannot have explicit loops. Explicit loops seem to just slow performance down to a crawl. They make the program unusable. So you need to make sure there's no loops. And the other drawback is that with cuPyNumeric, all of your calculation will go to the GPU. So you don't have a choice. It all has to be on the GPU. Whereas CuPy does allow you to decide what stays on the GPU and what stays on the CPU. And we'll see how that matters shortly. So I'm just going to show you the cuPyNumeric code. It's exactly the same as NumPy code, except that instead of importing NumPy as NP, I am importing cuPyNumeric as NP. And I also need to import a timing function, which this comes from Legit that I'm going to talk about in a second. But this timing function is GPU compatible, if you will. So if we time our linear solve with it, it will give us correct timing. So notice that the rest of the code is unchanged. I still have NP, but this NP will actually be calling cuPyNumeric, and that means that this function will be running on the GPU. The other little thing I had to change is that this Legit timing actually likes to return results in microseconds and not seconds. So you have to divide by 1 million to get results in seconds. So that's a little change which has to be done. But that's all you need to do with your code. But what about installing cuPyNumeric? So cuPyNumeric installs through Conda. That is the default installation. You can actually also do a source code installation, but it seems quite complicated and we would have to do it ourselves. So for now, cuPyNumeric, because it's quite new, NVIDIA released it just recently, it's not installed on our systems. So you have to do your own installation. And we don't allow Conda installations on our systems. I won't go into details why, but you can look in our documentation, search for Anaconda, and there's a long justification of why Conda is bad on HPC systems. But the way you can use Conda is you can install it through an Aptainer image, where Aptainer is an HPC-friendly analog of Docker. And users can build their own Aptainer images on our clusters. So I will just show you how to do that. So here is an image I want to build. So I put these instructions in an image.def file. So typically, you build an image by taking some pre-built image with all the essential things already installed, and then you add whatever additional packages you want. So here I want miniconda, so I get an image from some repository. That one seemed reasonable. You might find some other one. And then here are the additional things I want to install. But so post includes all the commands you want to run inside your image when you're creating it. Here, I actually want to check the Conda version and the Python version, which come from this image, which I'm using as the starting point. This can be useful because you might have problems if you pick an image which is old. So just make sure that when you get this image, starting image here, make sure that CUDA is recent or that Python are recent. And then if you're not, then find another starting point. And then the actual commands to install cuPyNumeric and Legit, which is a prerequisite, are these. So you need to define this environment variable and then Conda install these packages and then install cuPyNumeric. And here I'm also installing matplotlib, which I was using for plots. And so that's your definition file. It's quite simple. Of course, if you needed more packages, you could put them here. And then to actually create this image on our system, I do module load Aptainer and then run this command, Aptainer build. The NV flag is to access GPUs. I'm not actually exactly sure whether it's needed at this stage, but might as well add it. And this command will take a good few minutes to run, maybe even half an hour, depending on how busy our systems are. But eventually, it's going to produce an image file, which will be relatively large, a few gigabytes. And then once I have an image file, I can just run that container. So for example, if I want to run a command in that container, it's obtain run --nv, name of the image, and then the command I want to run. And in this example, I want to run legit and check its configuration. I can also start a shell. So obtain shell --nv image, and this will drop me inside the shell. Now I will want to run this obtainer image inside on a machine which has a GPU. So it's very important to, if I, for example, want an interactive shell, I should start a Salog job which requests a GPU. Once I am inside that Salog job, I do module load obtainer, and then I start my shell. And the --nv flag, it's very important. It makes the GPU visible once you are inside your obtainer image, so inside your container. So it's quite important to add it. So of course, you can also run obtainer inside the job where you get a job which can use a GPU, and then you run this, and then whatever command you want, Python, and then the name of your code, for example. So let's talk about Legit. Legit, it's NVIDIA's framework for distributed accelerated computing. So the goal is to take serial code, either unchanged or with minimal changes, and execute it in parallel on multiple CPUs and GPUs. So in the results I'll be showing, I'm just going to be talking about running on a single GPU. Part of the reason is that I actually don't have a multi-GPU example working. It seems that you need to compile Legit from source with QSolver to make that work. Well, I mean, you have to combine cuPyNumeric with a multi-threaded library. So I haven't done that, but it is possible. So this, of course, is a very nice feature, because if you're going to some really, really large matrices, you could think of distributing them on multiple GPUs, and this would be done automatically. So you would just take your normal NumPy code without any changes, and Legit and cuPyNumeric would run it on multiple GPUs, which is quite nifty if that works. So how do I actually run my cuPyNumeric code? So inside an interactive job, I would request a GPU for Salog, load obtainer, start my obtainer shell, and this drops me into a cursor inside this image. So here I'm going to define this variable, which is helpful because it makes Legit tell me what the configuration is. And I would run my code with, so you use Legit as a launcher. You say how many threads you want, and then Python, and then your cuPyNumeric code. So why do I specify OMP num threads? So generally, Legit, when you launch it, it makes a guess at how many resources are available. So it will detect how many GPUs you have. In fact, when you define this variable, Legit tells you, it will actually print out the configuration it's seeing. Unfortunately, it seems to be rather bad at guessing the number of threads it should be using. I think it uses some weird logic where it looks at the total number of threads available on the node, which is not what we want, because when you launch a job, you only get a subset of them. So here I'm actually telling it to only use one thread. So this avoids that problem, avoids some annoying error messages. And if you want to run cuPyNumeric inside the job script, you again do module load obtainer, and then obtainer run, name of your image. So here, of course, you have to point to the actual location where it is, and then Legit, use one thread, and then Python and test.py or cuPyNumeric test.py, whatever file you're using. So it's fairly simple, and things should just work as long as you request a GPU job. So what is the performance? Essentially, the performance is the same as with CuPy, very close. So it's clearly they're using the same library behind the scenes, but we are achieving this performance without having to modify our NumPy code. So with CuPy, we had to add additional lines, move data between the GPU and the CPU. Here we don't. But there's a little price we have to pay for this. Notice that my code actually crashed for n equals to 32,000. I was getting an out of memory error. This is because now my entire calculation is on the GPU. So in particular, even when I am initializing my matrix and I create this, so when I create, going back to this code, when I create this identity matrix, which of course, and a 32 by 32,000 matrix, that's a fairly large matrix, taking up 8 gigabytes. And of course, also behind the scenes, these libraries create intermediate matrices, which also have to be stored. And here, everything has to be on the GPU, and the GPU has only 40 gigabytes of memory, whereas on the CPU node, I can request more memory than that. So yes, this code now can run entirely on the GPU, but the price for this is that I hit the memory limit earlier. Now, there are ways to fix this, various tricks to reduce memory usage, which I will not get into here, but nevertheless, if you are using cuPyNumeric, that's something you have to worry about. All right, and finally, the last slide. So hopefully I have convinced you that GPUs can provide a huge performance boost to your NumPy programs, and CuPy and cuPyNumeric offer 2 easy ways to convert your code to run on the GPU. But the key thing is that the problem size for your problem must be large enough to make GPU use worthwhile.